So we have an exam coming up on Thursday. And as I mentioned in the previous class meeting, that's not right. I didn't put all the information on there. So it is going to be on, yeah, the date's right. So Thursday, October 1st. But the thing that I wanted to carry over from the previous slide is that the time of it is from 10:30 until 12:30. So I guess I can just type that in now so that you've got it in your ears and in your eyes. Time, 10:30 a.m. to 12:30 p.m. So you'll have a 2-hour block that it's available, but expected duration, I'm writing it as a 45-minute exam. And what that means is I think that about 3/4 of the class could finish in about 45 minutes. You know, like if we were in the classroom together and if I handed out the paper test to you, I would expect that 3/4 of the class would be finished in 45 minutes. Now, why not the whole class finished in 45 minutes? Because, you know, not everybody knows the material. And the people who don't understand the material aren't going to finish in 45 minutes. They're just going to use however much time you give them. So that's why I say that. But even though you've got a 2-hour window, I'm still going to make it a shorter exam. It's just I wanted to give you a little bit of extra time so that if you're going to print the exam, then you'll print it out. You know, you can leave it on the screen and just solve the exam on a blank piece of paper. But then what you're going to do is you're going to use CAM scanner or your flatbed scanner or however you create PDFs, and you're going to upload your PDF file to Blackboard before the exam closes at 12:30. Now, don't make the mistake of working on the test until 12:29 and then leaving yourself with a single minute to scan and upload the PDF file. I'm not going to be sympathetic to students who don't submit the exam on time. When I'm giving you 2 hours to do what I think is a 45-minute test, and I'm sure that there are students who will finish it in 25 minutes. You know, if you go over the allotted time, then I'm not saying that I'll throw your exam out entirely, but it will have been better if you just submitted it on time, that's for sure. So the coverage is chapter 2 and 3 in our textbook, the beginning of the semester up to and including the information that I'm sharing with you today. It's going to be problem solving. There won't be any short answer questions. There won't be any multiple choice questions. It's all just pencil and paper problem solving. You're not going to need to use Excel for the exam. And the equation sheet is available now. You know, here's the equation sheet that you can find on Blackboard. You're also allowed to use your previous homework assignments that you've solved, and so you can refer to them. You can refer to your textbook. In my experience, though, that can create a false sense of security where students think, oh, I'll just look it up in the book. I won't bother studying or learning in advance for the exam. So, you know, since it's a take-home test, I recognize there's not a lot that I have control over during the exam. So, you know, I concede that, yes, you can use your homework. Yes, you can use the exam. I will insist, though, that you work individually. And so you shouldn't consult with any student during the test. What you submit should be only what you have solved. So are there any questions related to the mechanics of the exam or my expectations? Any questions at all? Well, if anything occurs to you between now and then, feel free to call me on Teams or send me an email and I'll be glad to respond. All right, so today we're going to continue talking about buoyancy, which was a topic that was introduced in the recorded lecture from last week. And we're also going to talk about a related topic of the stability of floating bodies. And for those of you who are taking the Civil Engineering 319 lab, that's the experiment that we're going to do this week, is we're going to look at the stability of floating bodies using that same boat from last week, that floating apparatus. All right, before we move into that material, I just wanted to show you this image and give you some practice interpreting geometry, because in my past experience, sometimes the students understand the fluid mechanics, but then get tripped up on things like calculating angles or interpreting drawings. And so to try and prevent that as much as possible, I wanted to go through this illustration of what if we're looking at a submerged plate, and we have both a front view and a side view, as is indicated on the screen there, and then the dimensions are provided as shown. Okay, so take in for a minute what you would see from the front view, and then from the side view you can see that it's not a vertically oriented triangular plate. This triangular plate is in the water at an angle. And so consider what that means if it's at an angle when the question is, what are the dimensions of the triangle? So what's the size of that submerged plate? In the past, when I have given problems similar to this on like an exam, for example, sometimes students would make the mistake of saying that the triangle is 95 centimeters wide and 110 centimeters tall. So why isn't, is anybody willing to chime in either with your microphone or type in the chat box, why is it that this triangular submerged plate isn't 95 by 110? It looks like it's 95 by 110 based on the front view, but why is it not that?
Because of the perspective.
Very good. So what do you mean? You're exactly right, but can you expand a little bit by what you mean?
So from looking at this, the 95 centimeters would be right, but the 110 would be wrong because of how the image is tilted in the side view.
Exactly right. Yeah. So 110 centimeters is the vertical component of that triangle's length. If the width of the triangle is 95 centimeters, as he just mentioned, that's correct. But the 110 centimeters is just the vertical component of its length. And Reagan also chimed in, the base is the further away from the tip of the triangle. That's right. So, you know, the distance, the actual distance from this top down to the tip, it's not 110, it's going to be longer than that. And so the way that we would calculate the actual dimensions of the triangle is you'd need to know this length. We want to know, 95 is the width, but what is this length? And so from the front view, we get the vertical component of its length. From the side view, we get the horizontal component of its length. And then we could calculate its actual length with the square root of the sum of the squares. So here you can see the calculations. If it's 110 centimeters in vertical, 200 centimeters in horizontal, then that means that the actual length of that triangle would be 228 centimeters. So the take-home lesson of this real quick illustration is just pay special attention to the views that are given and think that the physical dimensions of the object may not be the same as the dimensions that are given in each of the views. All right, so any questions about that quick illustration?
Could you go back to the solution really quick?
Absolutely. Yeah. Here it is.
Okay, so on the magnitude of L, was that a typo?
I think that must be a typo. Let's check the numbers. Yeah, I'm astonished that that typo is still in there. Let's see here. So 110 squared and then 200 squared. Add it together and take the square root. I think my numbers are right, but just I didn't write it correctly. So let me change that now. Thank you for noticing that. I appreciate it. I'm always looking to ferret out these little bugs. And so it should be 110. And this is still correct. But I had just written 100 when really it's 110. Does that answer your concern?
Yes, thank you.
Okay. Yeah, great. And thanks again for noticing that. All right. So now let's move on to buoyancy. And what did we learn last time about buoyancy? We learned that the buoyant force is equal to the weight of the water displaced. So anything that's below the water line is going to be pushing water out of the way. And so in the case of this barrel, if this barrel wasn't in the water where it is, water would be in that same space. And so the barrel is pushing water out of the way. And so that means that the force acting upward on the barrel is going to be equal to the volume of the water that's been displaced multiplied by the unit weight. So remember, V sub D, the volume displaced, is just going to be what's the volume under the water line. So here, this barrel is fully submerged. So what I'd like you to calculate is, first of all, just as practice or refresher, what's the buoyant force? And then point number 2, if it is 1,600 kilograms in this barrel, and what we have is the length of the barrel, the diameter, and then the submerged depth. And that submerged depth, just as a hint, is just a little bit of a distractor, because how deeply submerged it is does not affect the buoyant force. The magnitude of the buoyant force is independent of how deeply submerged it is. So I gave you that 5-meter dimension, but you don't always need every dimension that's given in a problem. And sometimes in your engineering career, in fact, most of the time, the information that you're going to get is irrelevant. Like if you look at the number of things you could measure and the information that non-engineers will give you about a particular scenario, you're going to have loads and loads of irrelevant information. And part of what you're having to do as an engineer is identify what's important and what's not. So here is some unimportant information, how deeply submerged it is. But what it is important, the diameter of the barrel, the 180 centimeter length of the barrel, and then the mass. All right, so let me bring the equation onto this screen in case you don't have it from last time, that the buoyant force is equal to the volume displaced multiplied by the unit weight. So let me pause for a moment and give you a chance to solve these two questions. And then, of course, as I always do, we will, after a few minutes, take a look at the solution on this one. All right, so we want to compare the buoyant force and the weight. Now, first of all, the buoyant force is going to be the volume displaced multiplied by the unit weight. And this is submerged in water. We don't know the temperature of the water, so we'll just use the typical unit weight of 9810 newtons per meter cubed. What about the volume displaced? How do we find the volume of a cylinder? Well, it's going to be the area multiplied by the length of the cylinder. So we can calculate the area, the face area of that circular part, by pi d squared divided by 4. So we are given the diameter, so pi times this 2-meter diameter squared divided by 4 gives us the area, and then we have to extend that by multiplying the area by a length, and that gives us the volume. So you multiply it by 1.8 meters. All right, so the barrel volume is 5.65 cubic meters. And so here you can see that I had the area times the length of the barrel, where the length is 1.8 meters. Now, this is why I think it's a great idea to always write your units as you're substituting numbers into the calculation. This semester, I don't think you're ever going to see an example from me where I just write the numbers without the units. Every single time I'm going to write the units, because what if I had accidentally written 180, 180? I mean, that's going to totally change things. And the length is 180 centimeters, and so if we divide 180 centimeters by 100, because it's 100 centimeters per meter, then we get 1.8. So the point is, I think it's a great idea for you to always write the units as you're solving calculations, because sometimes if you just focus on the numbers themselves, maybe a person would be tempted to write, 2 for D and then 180 for the length. And then that would be mixed units. Like if you have meters squared multiplied by centimeters, then suddenly your volume is going to be all wrong. So that's my hint for this first part is substitute the units in when you're doing the calculation. So the buoyant force then is going to be the unit weight multiplied by the volume displaced. So any questions so far on calculating this buoyant force? All right, so what about the weight? How are we going to know the weight of this? Well, we have the mass of it. And so if we multiply the mass by g, and that gives us the weight. And comparing the buoyant force to the weight, the buoyant force is bigger. So what we're looking at right here is just a snapshot in time. It's not yet in equilibrium. What this barrel is going to do is it's going to float to the surface, and it's only going to be, when it is in equilibrium, it will only be partly submerged. It will be the percent submergence for that barrel is the ratio of the weight to the buoyant force. Incidentally, we saw that in the last in one of the examples from our last lecture, that if you want to find out what percent submerged it is, you compare the weight and the buoyant force. So right now it's about to float to the surface, or maybe we took a snapshot as it's floating towards the surface because it's not yet in equilibrium right now. Okay, so any questions about that or any comments before we move on? All right. Well, this, on a cold, rainy morning here in Huntington, West Virginia, spending some time out on the water seems like it would be a lot of fun. Sunny day, sailing. I don't know if you can see as clearly on your end as I can on mine, but there's something below the water line here. And you'll notice that they're all sitting on the edge of the boat, and the boat is tipping over. But it's stable, though. It's not going to continue tipping over, even though the wind is blowing from the direction from the right towards the left. The wind is blowing on that sail and tipping the boat over, but because it has so much weight down below, beneath the water line, there's a lot of ballast. And we can kind of see it a little bit, but one of the design elements of a boat is that you put a lot of the weight down low to try and make it stable. And so that's what we're going to be talking about today, is some equations that we can use to analyze whether a floating body like this boat is stable and will naturally right itself, or what would it take in order for a boat to be unstable and prone to tipping over. So we're going to look at the method that's used to determine that. Now consider these two cylindrically shaped objects. On the left is a submarine, and on the right is like a log, kind of like a game that you'd see maybe at like a beach or something. And they're similar in a lot of ways. They both have people standing on them. They're both cylindrical. They're floating in water. But it looks like the kid is struggling to keep his balance, whereas the people on the submarine are at ease. They're not struggling to keep their balance. And it's not just that the difference is size. There are other differences as well. The submarine is specifically designed to be stable so that it will float upright. And we'll talk about what they've done to the submarine to make it so that it is naturally and inherently stable. Consider this diagram. What we have is the center of buoyancy, and so C is at the center of the circle. And so the center of buoyancy is determined by the shape on the outside. It's not determined by what's going on inside the shape. And so the center of buoyancy is just based on the fact that this is circular and it's pushing water out of the way in a circular shape. But you'll notice that the center of gravity is a little bit lower, and that's because we have this ballast at the bottom. It's just a little bit of extra weight, and because of that extra weight, it has taken the the weight will naturally go down to the bottom. And from what I'm told, I don't wear contacts, but I've heard from people that contact lenses can be made so that they will always go into a certain orientation in the eye. Similar to this, they can be made so that even if you put them in crooked, then the lens will rotate in your eye and go into the correct position. I don't think it's because it has a big piece of steel at the bottom of the contact lens, but it may have some sort of a feature that causes it to naturally right itself. And what I mean by right is, if you were inside of this and setting a chair on top of this flat weight, if that was like the bottom of the submarine, you would consider it right if the weight was at the bottom. And if somebody came along and bumped it and caused it to rotate, suddenly you'd tip over and it wouldn't be right for a moment, but it would naturally go back to its stable position. So this is stable right now. And the reason why it's stable is because the center of gravity is below the center of buoyancy. So C is center of buoyancy, G is center of gravity. And the buoyancy is determined by the submerged shape, and the gravity is determined by the mass. So it's stable because even if you rotate it the other way, the G is going to naturally go to the bottom. G is going to be as low as it can. The weight will always be at the lowest point in that shape. If you roll it over, it will right itself, and that's what we define as stable. Now consider these other two alternatives. Now B, option B here, is neutral. Rather than being stable, it's neutral because the center of gravity and the center of buoyancy are in the same place. And so if we rotate it, it's not going to go back into its original position. But here in object C, this is showing what would happen if we took the one on the left and if we rotated it. And so if you did rotate it and you took the weight up here to the top, it's still going to right itself. And so it's currently in an unstable position, but it will move back into equilibrium because of what's called a righting couple. So see where it says righting couple in italics? Think of it this way. If you had a piece of paper in front of you with the printout of this screen, like if you just printed this slide, and maybe you did, maybe you have it in front of you. Put your finger on the letter C here on this image on the right, or you can just imagine this. Put your finger on C and put your finger on G, and then push up with C and push down with G. So push on this image in the direction that's indicated by the arrows. And so what would happen if you have a piece of paper, let's say, here's my piece of paper, if I push down on the right and I push up on the left, it's going to rotate it until it goes back into equilibrium. And so that is why it will rotate back into its stable position, is because G is down, C is up, and the direction of those forces, the righting couple, is kind of like it's what's causing the rotation. You can think of it in terms of maybe it's a moment because there's a distance between the two and the direction. But that righting couple causes the stability. And so it's not just submerged objects that can be made to be stable. Even boats that float at the surface can be made to be stable. But this is an obvious case of stability. If C is above G, then you will have a stable body. Here's a more complex shape, and it's not fully submerged. And so let's ask ourselves, is this stable or unstable? Now in the previous example, G was below C, and that's what made it stable. But what I'm going to show you on this next one is that even when G is above C, it can be stable, although there's a limit. Now think about, first of all, why would the center of gravity be above the center of buoyancy? And so think about what causes, like why is the center of buoyancy where it is. And so C, its location is determined by the shape underneath the waterline. So if you just think about what is the midpoint of the area under the waterline. So C is just kind of like the middle, the center of area for the submerged shape. That's C. G, on the other hand, isn't determined by the submerged shape. It's determined by the mass of that boat. And some cargo ships, if you've seen like video or maybe even in person, if you've seen a container ship, sometimes they'll have layer after layer after layer. They may have 10 or 15 stories of those metal shipping containers on the deck of the boat. And so that can bring the center of mass very high. And so that's kind of the case here. We have this cargo boat, and the center of gravity, G, is relatively high because there's so much mass above the waterline. Now they still are going to put some ballast below the waterline, but the location G isn't dependent just on the shape beneath the waterline, but it's dependent on where is the mass in the boat. Think about if this ship tips over, what happens is the center of buoyancy is going to change. And so it's in the center right now. C is in the center because the ship is upright. But when it tips over, now there's more area on the right side that's submerged than on the left side. So look at this triangle, A, B, O. So that used to be submerged. The area A, B, O used to be submerged when it was upright. But now that the boat is tipped over, all of that area that used to be on the left side is now on the right side. So there's more submerged area on the right side of the boat. And so tipping over doesn't change the boat's center of gravity necessarily. You know, like if the cargo is rolling around, then that's going to change the center of gravity. But let's just assume that these guys are ship shape and they batten down the hatches and all that stuff so that their cargo of bowling balls isn't rolling around. It's secure. And so that means that even when the boat tips a little bit, the center of mass stays in the same place. But what moves is the center of buoyancy. So that's why C is now in a different location. All right, now that thing that I did with my fingers earlier, do that mentally or, on paper. Put your fingers on this boat and push down at G and up at C. So if you think about what that's going to do to the boat, that righting couple is going to cause the boat that's tipped over right now to come back upright because there's more buoyancy on the right side. And so since there's more buoyancy on the right side than there is on the left, it will cause the boat to come back into stability. Now there may be wind or waves that causes it to slop back and forth and back and forth. And maybe people are going to get queasy on there, but it's not going to tip over. It's not going to be a complete loss as long as it's stable. And so there is an important location that we have to be aware of, and that is location M. Location M is the meto-center, and that's the location that the center of buoyancy is always pointing at. And so think about in this image on the left, the buoyancy is pointing upward, and M is up here, the meto-center. But now if the boat tips over, the location of the center of buoyancy moves to the right, and so it's still going to be pointing up, but M is kind of like an axis of rotation. It is the axis through which all of the buoyant forces are pointing. So the meto-center is the point of intersection of the lines of action for the buoyant force before and after tipping. So in other words, C always points at M. So if we tipped the boat over even a little bit more, so it's tipped over, what does that look like? Maybe 10 degrees or something. If it tipped over 35 degrees, then that would push C even further to the right, but C would still be pointing upward towards the metacenter. By the way, I spent a couple of weeks on a boat one time. We got in a big storm, and it was going back and forth through 35 degrees and up and down through 15 degrees. And that was for like 3 solid days. It was miserable. Never go to sea. It's the worst. All right. So any questions so far about this information on stability? The metacenter is where the center of buoyancy is always pointing at. All right. So that's what makes it stable, is this righting couple. G is going to be down, and it's to the left of C, and C is going up, so that'll bring it back into equilibrium. Joseph asks, would C be pointing at an angle or still vertical? It would point straight up, but its location will have moved, and so it's kind of like the center of buoyancy will be shifted to the right, but the whole boat is at an angle. So the C is always pointing upwards. Great question. The metacenter stays in the same location. I wish I could physically move this image. And so like if the boat is tipped over more, C moves to the right. But because the boat is tipped up, even though C is over here, this is going to be now up. You know, from here up to C, up to the metacenter will be vertical because the entire boat will be tilting. And so C will be pointing up. The metacenter stays stationary. It doesn't move. So it's not accidental that ships don't tip over. I mean, it's by design that the ships are intentionally designed to be stable. And so the rule that we can say here is that if M is above G, then the object is stable. So if the metacenter is above the center of gravity, then it's going to be stable. So we want to know what's the distance between M and G. If the metacenter is below G, that's when we're in trouble. If G is above M, then it would tip over. Now think about what would make G go higher. Like, let's say that these guys are carrying a cargo of bowling balls. And a lot of the bowling balls are down below the waterline, and so that's the ballast. If they moved that cargo of bowling balls from below the waterline and then they like put it up in the top of the ship, that's going to make it more tippy, right? So if you have lots of mass up high on the upper deck, that's going to make the ship more prone to tipping over. And so if you took the center of mass higher and higher and higher, once the center of mass goes above the metacenter, that's when the ship is going to be unstable. So just think about in physical terms, like it's easy to get hung up in the equations I'm going to show you on the next screen, but really try and think of it in real physical terms, like why is G where it is, and what could you do to change G? Like if you take the cargo down low, then that makes G further away from the metacenter. And the further apart those two things are, then the more stable the ship is. If you have your center of mass real low, then you're going to have a very stable ship. But if you take the center of mass higher and higher, so you've got one of those cargo ships with containers, if you keep adding another layer, and you just keep getting taller and taller, then it's going to be too tippy. So in order to do these calculations, one of the things we're going to have to look at is the area moment of inertia. And here's a barge, and you can see that it's the shape that the barge makes with the waterline that defines our area moment of inertia. And so the width of the barge, the narrower parameter, is going to be B, which is what we cube. And A, the longer parameter, like the length of the ship, is going to be the A parameter that we just take to the first power in this equation. So the shape that this barge makes with the waterline is that of a rectangle. When you look down from above, the area moment of inertia that we're talking about is the axis of rotation from the front to the back. So how tippy is it, in other words? So now think about a canoe. You know, a canoe isn't as wide as a barge. And so it's going to be easier to tip over a canoe than a barge. And so one of the factors that determines how stable a floating body is the width. That's going to be one of the factors. And so maybe if you've been to Hawaii before, or you've ever seen a video of like the Hawaiian outrigger canoes, like it's a canoe that someone's sitting in, and then there's kind of like a log over on the right side of the canoe. And they put that log out in the right side of the canoe to try and make the canoe effectively wider than it normally would be. So that increases the area moment of inertia, and it makes the floating body more stable. All right, so here's the equation. We want to calculate the distance between G and M. The question is, how far apart are they? Is G below M? Good. Then that means it's stable. If G is above M, that's bad. It means that we have an unstable body. So the way that you calculate the distance is with this formula. And so what makes you have big stability is like a nice wide boat. And so if you have, for example, a large I, a big area moment of inertia, then that's going to give you loads of stability. But what decreases your metacentric height and makes your boat more unstable is the CG. So CG is the distance of the center of gravity above the center of buoyancy. And so remember, if you have that ship that has lots of mass up high in the tall upper decks of the ship, that's going to make GC increasingly large. And so CG is how far, and by the way, these are physical measurements. This is like in units of meters or centimeters. It's units of length. And so CG asks, what's the distance from the center of gravity to the center of buoyancy? And the criteria that we'll apply here is that if we have a positive GM when using this formula, then that means it's stable, and a negative GM means that it's unstable. So there's the two components of calculating the GM. There's the first term, which is the area moment of inertia divided by the volume, and that's just the submerged volume, by the way. So that will give you one parameter of length. And the bigger this first term is, the more stable our body is. And so what's really stable? A wide boat that is very shallow, that has very little submerged volume. So think about like, have you ever been to a lake that had like a floating dock? A floating dock is kind of like a boat in a way. It's a really wide boat with a very shallow draft. But the deeper the draft of the ship, that's going to increase instability. And then also what makes it unstable is having the center of mass up high. Okay. So in other words, a big I to V ratio promotes stability, and a large C to G promotes instability. Let's look at this example. Now this is something that I emailed you the PDF just a couple of minutes before class, and I wonder if there's a way for me to also share it here in the browser. Yeah, share files. Let me also send it to you through this Blackboard. Let me just browse to the location. If you can print this out, it's fun, I guess, to solve it having the paper in front of you. But if you just are going to solve this like it's a normal example, then that's okay too, just like on a scratch piece of paper as we look at it together. But this is lots of steps here, A through H. And, all right. Oh, okay. Well, this is just a different way of looking at it. That's not so fancy. I'm going to go back to my screen. All right, that's better. Okay, so let's consider the dimensions and take a look at what's given here. It's a 6-meter wide barge, and so you can see that's looking at it from the front. 6 meters is the width, and it's 15.25 meters long. So let's go back to this other barge that I showed you earlier. This one. Okay, so in our example, it says the barge is 6 meters long, so that's B. And then it says that the barge is 15.25 meters long. So that's A. So A, its length is only going to be to the first power in this area moment of inertia formula. And then B, its width of 6 meters is going to be cubed. Because what we want to know is I, the area moment of inertia about the water line. All right, so that's just a quick preview on how we're going to calculate I. But first things first, we know the combined mass of the barge plus the load that it's carrying. And it looks like it's carrying rocks. So, you know, this is something we see on a pretty ongoing basis here in Huntington. If you ever look at the river, you'll see barges full of coal going up and down that river continually. And so let's say that this is coal. It's not rocks, it's coal. So the combined mass is 181,000 kilograms. So step by step, what I'm asking you to do is calculate each one of these things because it's leading you towards the assessment of whether it will float upright because it's stable or whether it'll tip over because it's unstable. And so remember that what we're trying to figure out is GM positive or is GM negative? So you're going to calculate I, and you're going to calculate V, where V is just the submerged volume. So what's the volume underneath the water line? G is already, we know where G is located. Just coincidentally, it looks like the center of gravity is up at the top of the barge. What we want to find out is where is C, the center of buoyancy. And I've told you that let's say that D is the depth of submergence. So from the buoyant force, you can say that the buoyant force is equal to the weight. It's floating in equilibrium. So A through H, I ask you first to think about the weight, and then in step B, in equilibrium, the buoyant force will be the same. All right, so I'm going to stop giving this away. I'm already giving out too many hints just because I'm so excited. So I'll pause for a moment, give you a chance to start running through these calculations, and then, of course, we'll take a look at it together in just a moment. All right. So some people have made it to the end. I don't expect that everyone has. You know, we all work at a different speed, and that's fine. I myself am actually a pretty slow calculator. So I was always grateful that at my university, we often had unlimited time on exams, if you can believe that. At my university, there was a testing center where you would go and take the test at any particular time that was suitable for you. You know, your professor would put the test in the testing center, and then you just go over there like it would be open for 2 or 3 days. And some of those exams we had unlimited time for, and I got used to that. I don't know where that distraction came from, but the point is, let's look at these calculations. Here we go. So we've got this ship, and we want to find out, is it going to be stable or is it going to tip over? Okay, so first things, you'll notice that I just kind of put C, the center of buoyancy. I drew a little, someone needed their broccoli. I'll always take broccoli. Actually, I took candy into the exams just so I'd have plenty of energy. I should have taken broccoli though. All right, so C, the center of buoyancy, I've just kind of drawn a little dot to indicate where that is. Now, at this point, I don't know how big D is at the beginning because I haven't done any calculations yet. But what I can say is by inspection, C is halfway between the water line and the bottom of the barge. So that distance, D, is the depth of submergence. The physical height of the barge is 2.44 meters on the edge. That's how far it is from the bottom up to the top edge. But D is the depth of submergence. And what I'm saying is the center of buoyancy is at half the depth. Okay. So first, what is the weight? Well, if the mass is 181,000 kilograms, then we can calculate the weight by multiplying that by G. So 1,775,610 newtons is the weight. And if it's in equilibrium, then by definition, the buoyant force is equal to the weight. Okay, so the buoyant force and the weight are equal if it is in this equilibrium. So then how deeply does it sit? Well, what we know is that the buoyant force is this. So the buoyant force is equal to, here's our formula for the buoyant force, and that's going to tell me how deeply submerged it is. The only thing I don't know is D, the depth of submergence, because I know the width of it is 6 meters, and the length of the barge is 15.25 meters, and the unit weight of this being water is 9810. So I can rearrange that equation in terms of D. So D, the depth of submergence, if it's this loaded down, then it has to be 1.978 meters submerged. And if we poured in more coal, then it would sit even deeper in the water. And if you sit by the river and watch the barges, and you can tell if they're loaded or not loaded, because if they're loaded, they're really down low. It looks like a splash is going to send water over the side. But if they're unloaded, then they sit with a very shallow draft. They're up much higher in the water. So in this case, just based on the weight tells us how deeply submerged it is. And so here we calculated D. Now, step D says, draw a sketch of the barge from the top view. So the reason why I asked you to draw it from the top view is to help you calculate the area moment of inertia correctly. And so the width parameter, the smaller dimension of 6 meters, is going to be what we cube in the area moment of inertia. And the length of 15.25 is what we take to the first power. So the area moment of inertia then 274.5 meters to the fourth. Now, any questions so far before we get any further? Anything you want to ask about? All right, then let's now look at calculating the distance CG. Now this goes back to the first thing. We want to know CG. Well, I just calculated D, and the hint I gave over in the chat box is that the distance from C to the bottom, so C to the bottom is 1/2 of D, right? So then 2.44 minus this distance will give you the length from C to G. Okay, so we have D, the depth of submergence, half of that, and then subtract that amount from 2.44. So where did I do that? Oh, here. In this sketch, I'm saying it is 462 above the water line, and beneath the water line is 0.989 meters, and so then that means that the distance CG is going to be the sum of those two, so 1.4 2.451. That's a little inelegant, that drawing, and also how I calculated it. I'll do that different next semester. But you can see now when I substitute in the area moment of inertia, the submerged volume, then what's left over is a positive amount. So this is a stable barge. It's not going to tip over because GM is positive. So it's stable even though the center of mass is above the center of buoyancy. That's okay, because what happens, think about, if this starts to tip, there's going to be more submerged volume on the right side, which means that righting couple will set itself up. C is the center of buoyancy, and so the center of buoyancy would move to the right, and the center of gravity is still acting straight down, and so that would cause it to tilt back into stability. Can I go over the center of gravity again? So you mean like the calculations for where it is, where it's located? The way that I determine where C is we calculated D, the depth of submergence, based on the buoyant force. And so the key of knowing where C is actually starts in calculating D. So we calculate D based on how heavy the barge is and what we know its weight is. And then C is just going to be in the middle of the submerged depth. And so 1.978, if you calculate 1.978 divided by 2, so 1.978 divided by 2, so that's 0.989. So back over to this sketch here. See here, I'm dimensioning the distance from C up to the water line. So that's just saying the 1.978 split in half. There's half of that distance above it, half of the distance below it. And then this dimension of 2.44 from the top edge to the bottom is then how we find out the distance from the water line up to G. So in other words, 2.44 minus 0.989, I'm just doing this on my calculator, yep, is 1.451. So the distance CG. All right, so it's stable. Are there other questions related to this example? Did I include this in your notes, this slide? I need to hide this slide so that it's not in the notes. Takes the fun out of the example if you've got it right there in front of you. All right, any questions on the stability before we just look at one kind of unusual application of hydrostatic forces? Okay, well, this is an illustration of what if the gate that we're interested in is above the water line. In many of the previous examples, the gate was below the water line, but let's look at this image and try and think about what's going on here. Here is some water, atmospheric pressure air above it. And so what that means is if we follow that water line over to the left, this is zero pressure at the interface of the air and the water. It's zero pressure here. And so if you go over to the left, it's still zero pressure. And then what if we now start going up? So we're going up through the water. That means that now the pressure is becoming negative in terms of gauge, not in absolute terms. You know, here at the interface of the air and the water, the absolute pressure would be 101,325 newtons per square meter. But in gauge pressure, it's zero. So in other words, we're going up through the fluid, the pressure is decreasing. And so what that's going to do is that's going to suck the gate in towards the liquid. Instead of the water pushing out on the gate, here, since it's a negative pressure above the water line, it's pulling the water down, it's pulling the gate down towards the bottom. So if you were going to find the forces here in this kind of an illustration, find the forces that are horizontal and the forces that are vertical, what I'm going to show you in just a moment is the calculations that we'd go through to do that. To find the horizontal force, you would make a vertical projection of the curved gate. And so here you can see it's got a 3-foot radius and a 2-foot width, meaning into the page that gate has a width of 2 feet. So the vertical projection of that is 3 feet tall and 2 feet wide. So the horizontal forces are going to be using that, but the pressure is going to be negative up above. So the force horizontally is going to be pulling the gate to the right. And then for the vertical forces, it's the weight of the water, and not the weight of the water above the gate, but it's the weight of the water below the gate to the water line. So this is kind of a specialized case where we have negative pressure, and it kind of flips our perspective on how things are normally calculated. So I just wanted to show you how we would go through the calculations for this one. So for the horizontal force, then we still use pressure at the centroid times area. And the pressure at the centroid is going to be some delta H times the unit weight. And so let's look back at the image again and see if we can agree on what would be the delta H. Okay, so in the dimensions here, it tells us it's 1 foot from the water line up to this edge where the gate begins. And then the vertical distance of the gate, if this is a vertical projection, then it's 3 feet tall. So what is the distance from the water line to the center of area of the projection? So the center of area is going to be, like 1.5 feet from this dot to the center of area. So 1.5 plus the extra 1 foot that takes you from the water line up to this other dashed line that corresponds with the edge of the gate. So that's why I'm saying the delta H that we would apply here is 2.5 feet, but the distance minus is because we're going up rather than down through the fluid. The unit weight of this fluid is defined as a gamma of 50 pounds of force per cubic foot. And so here we're saying it's a distance of 2.5 feet, 50 pounds per cubic foot, and then the area of the gate is 6 feet because the vertical projection looks like it's 2 feet wide and 3.5 feet tall. So the horizontal force is going to be that the water is pulling the gate to the right with a force of 750 pounds. A very unusual case, but we can still apply the same methods. And remember, for vertical forces, we've always thought of it in terms of the weight of the water. And normally what we'd say is it's the weight of the water above the gate to the water line. But here, it's the weight of the water below the gate to where the water line would be. So think about what are the shapes that we have here. There's a wedge shape, and then there's a rectangular box. And so the wedge shape is 3 foot radius multiplied by 2 feet into the page. That will give us the volume of that wedge, and then there will be a box shape that's 3 by 1 by 2. If you can think about what will be the shape of that piece. And so the weight of the water, here I've done my best, which isn't saying a lot when it comes to hand sketches. We've got this wedge shape, and we can calculate the volume of that. It's the area of a quarter circle multiplied by the 2 foot width of that piece. And so here's the volume of just that wedge piece. And then there's the volume of the rectangular box. And it has a volume of 6 cubic feet. So if we add those two volumes together and then multiply it by the unit weight of the fluid being 50 pounds per cubic foot, then the vertical force would be pulling the gate down with 1,006 pounds. And so the two forces is that the gate is being pulled to the right and it's being pulled down. So because it's a suction, since we have negative pressure up above here, that's pulling the gate in towards the water. So if we think about what kind of a connection would you need where the gate is welded or attached to this frame that it's in, you need to give it the strength to push up on the gate and to push the gate to the left to resist the forces that are being experienced by the gate. All right, so that's just a little bit of an application of how we deal with negative pressures. So if we have a hydrostatic force, vertical and horizontal, if we're above the water line and the pressures are negative. It's 12:13. We are out of time. Let's briefly revisit these announcements and remind ourselves that we won't have a live meeting on Thursday because you will be taking the exam. The exam will be available on Blackboard at 10:30, so I won't email you the exam. You'll have to go to Blackboard to get it. And you can print it out if you like and work on the paper, or you can just display it on your screen and work on a blank piece of paper. The format is just problem solving. The equation sheet's there. If you have any questions as you're studying, just give me a call on Teams or send me an email and I'll be glad to talk to you. Otherwise, good luck on the exam, and we'll have a normal class meeting next week on Tuesday of next week. And I guess I'll see many of you for lab today or tomorrow, those of you who are in Civil Engineering 319. So that's it for today. Take care. Bye-bye.